Alrighty then. So this is going to be my video presentation for the project of the graph start begin project whatevers. To begin with, I went through and I commented through all of the various headers of the class abstracts, and you can see them all here. I just basically went through and commented on them. The only big sticking point I have with this is that the UID for a given node is whatever its data is. And well, the data is not publicly accessible. It has a void set data, which can actually change it later on, which is not a good thing because if you look here at the void set data method, you can actually see that it is very easy to swap out later on, and there's no check to make sure that it's not using an identical ID to an already existing node or vertex. But you know what they say. Trees are just graphs with dead ends. But yeah, so I just went through. The data is the UID of whatever the node is. Then the other thing is you have a private list of the vertexes, which are whatever the connected vertexes are, which is kind of strange because it's pointer to pointers. Don't ask. But yeah, then down here you just have the public constructor, the public overloaded constructor, which allows you to start off with at least one vertex, or to load it into as you're making it. This one just destroys the vertex. This one adds an edge to the vertex. Huzzah, huzzah. Pushing it into the list. Yeah, this one just runs through and looks to see if there's a connected vertex and checks to see if there exists an edge to connect to the vertex. It's kind of strange. This one just removes an edge. This one just returns whatever the data is, UAT. And here's the node-based graph, which is, you know, awesome. This is actually just a list of the graph itself. It's a container list for the nodes within it. This one's just the basic blank constructor. This is the overloaded constructor. This is actually the one that I use, which is ironic because it just calls the regular one, and then it inserts whatever your initial vertex is, which means you have to declare a vertex and make a vertex prior to creating the class if you want to use this one, which I did. And I know technically it says we're supposed to use every method or function of it, but since this is the only operation inside of this one, and the same line of code is repeated right here, I don't need to use this one because it is using that one. I could replace this with that and it's identical. The deconstructor, it just destroys everything. Huzzah. This node inserts a new vertex node within the graph. This adds a vertex to the graph from an already existing instance of a vertex. This one actually creates a new vertex and then pushes it into the above method, which I completely point out right there. I call them overloads. C++ people call them overrides, but I'm a .NET developer, so I call them overloads. Yeah, terminologies. But yeah, this one uses the UID to remove a given vertex. So you send in whatever your unique identifier is. If it's an integer, if it's a double, if it's a letter, it doesn't matter. And then it goes through and it finds the vertex, passes it as a pointer, then passes that down into the remove vertex, and then remove vertex goes pop and kills it. So graph remove, vertex to remove, goes from here, points down to here, points off to the graph, and pops it off. This orders the graph to add an edge between the starting vertex and the ending vertex. So this basically just creates a connection between two different vertexes, kind of like a linked list or a binary search tree. This only works one way. A very easy thing, and I'll just type it really quick right here. But if you did end underscore vertex dot add edge start vertex, just putting in this single line of code in the add edge would make it bidirectional, which would make your graph non-directional. Since if you put this in, you're creating a path that travels back and forth from both in one go. But hey, that's just, me. So I'll go ahead and take that out. Because I did single directional paths. You could also do the same thing outside of it, just transpose these two on the next line of code or whatnot, and you can make a bidirectional one on a case-by-case basis. Adding the end vertex dot add edge start vertex, the reverse of what this is, would make it so that anytime you use the add edge, it would be bidirectional. And most of the time you don't want that. But hey, you could also overload this and say like you could do start vertex, end vertex, comma, boolean bidirectional as your boolean statement, and then you could just have a if else statement inside of this, and then you'd be able to do, oh, okay, well, it's one directional, start vertex, end vertex. Or if it's true bidirectional, then it's just that double statement that I had typed earlier. Remove edge. This just removes an edge from the start vertex going to the end vertex. And that's very self-explanatory. This one adds an edge, i.e. a path. And this one removes a path. It's very straightforward. Is edge. This just checks to see if there is an edge between two. So it goes to the vertex, it searches for a specific edge. So let's say I'm on 1, I want to search to see if 1 connects to 12, I check to see if it connects to 12, well, with the way I have my graph set up, it doesn't. So there you go. But if it was like, say, 1 connects to 2, 1 does indeed connect to 2, so it would search 1 for connection to 2, and it would return true. So the Boolean return would be true. This is really simple. It's used in a lot of them. For every bit of the items in the graph vertex list, iteration, it will search it to see if you find the UID. So this is kind of like searching a database table for a unique identifier, and really all it's doing is going through the list, and if it runs into one that matches, it returns yes, it does, and a pointer to that vertex. This is one of the problems that I have with the UID being able to be changed after the vertex has already been initiated, because if you finagle with the data, you're changing the unique identifier for it. So I could say end up with 2 nodes that are actually 12 instead of one node that's 12 and one node that's 14. If I decided to change that 14 to 12, this would just return me the first 12 that it runs into, which is bad, which is very bad. If you can't find it, returns a null pointer. So anytime that you're using the find vertex and you're not absolutely 100% sure that it's going to find a particular node, you should generally check for null before you attempt to use it, because failing to check for null before you attempt to use it can lead to catastrophic system failure. Yummy! And this is just like the top one up here, but it's just like an overloaded version. This one searches on the basis of data. This one searches off of the actual vertex. It's like node defined. Well, you kind of somehow already have the node, but whatever. And this one just returns the size. So it just returns the size of the list that the class is using, or the instance of the class template. Raw. Graph adjacency. Graph adjacency is pretty much the same as node base, except it doesn't have all the same methods. And I had to write something in order to basically do the same stuff that print adjacency list did, but we'll get to that. So this is all the same thing. Contains list. It has a destructor. It goes ahead and does the add vertex. The interesting thing is this one's add vertex doesn't have a return, so it just adds it. And if it fails to add it, it gives you a C out. It doesn't return anything cool. And it doesn't even return an instance of the add vertex like this one does. So this is graph node base, and when it does the add vertex here, it goes ahead and okay. Oh, that's right, it calls it insert. Somewhere. Yeah, right here. It returns a vertex, whereas you can see with this one, it does not return a vertex. It returns a list of integers, which is definitely not the same as a vertex. Boy. But yeah. Other than that, you can see down here you have add edge boolean. This is another overloaded / overridden function or method or whatever the hell you wish to call them. This top one here accepts a vertex pointer argument and a data argument. The bottom one here accepts 2 vertex pointers. So pretty much the same functionality, with the difference of being that this one will actually create the vertex if the vertex did not already exist, which is kind of cool, because you can see it right here. New list T, new vertex equal add vertex data, new vertex push back data, and then it returns true. But if you're trying to pass one, if the vertex that you're trying to add the edge to doesn't exist, then it gives you this. This one, and this one's very straightforward. Do these both exist? No. Can't do that then. If they don't both exist and there isn't already an edge, because if this returns false because there is an edge there, and it doesn't work. So because it prevents you from adding duplicate edges. which is the whole point of this if statement right here. And if it doesn't have a duplicate edge, it goes ahead and makes an edge between those two vertices. But again, since we've already looked at the add edge, well, that is add edge. But since we've already looked at the various incarnations of the add edge, if you don't set it up differently for the vertexes, because this is actually based off of the base class for the vertex, which is vertex connected here. And here's the add edge. If you don't reverse it, the receiving edge doesn't see the sending edge. So it's a one-way path from the starting vertex to the ending vertex, or the second vertex. However you wish to prefer to say that. This just checks to see if it's vertex, basically checking to see if it exists. Again, this is just checking to see if an edge exists. This, again, just checks to see if an edge exists. This checks to see if the vertex exists. And this is the cool part. This is pre-adjacency. This is really nice because I had to do the same thing. Well, I felt inclined to do the same thing for the node-based graph. This just returns the number of edges on a given vertex. And this just goes ahead and lists the number of edges on any given vertex, which is also pretty sweet, but not really necessary, because you can see when you do the cout printout with the print adjacency list, you already can tell how many edges it has. And it would have to be pretty crazy before you would actually need to use the number of edges printout, because it just goes vertex size, which just tells you the size of the connectors for vertex, which is actually all the way at the bottom, ironically. Yeah. The vector. And then there's graph size. But that's really not that hard or surprising. Okay. So really simply down here at the bottom, because this is C++, main is always at the bottom, because that lets you treat everything else as a header. I just declare two booleans in order to receive the outputs from the boolean test methods or functions. Node-based testing, wham bam, thank you ma'am. It just runs through this, tells you the result of whether it passed or failed on a line, makes a new line, runs the next test, tells you the result of that test. Not rocket science. So here's our first test. Just go ahead and declare the beginning integer. This was where I was talking about the node-based graph and how it goes ahead and creates a new vertex, and then I push that vertex in before I initialize the graph node-based. I just felt like receiving it. I don't actually ever have to use it, but with the node-based, the graph that's node-based, it actually returns the vertices as it makes them, which is handy, and it's something I should get in the habit of handling because it's cool. But other than that, it just runs through a while loop, adds on to an integer. The integer is used to create the data that's then inserted into this graph. It's actually inserted into this graph, but this graph gives back the graph vertices. So I just have the nodes stack those up in a list. And then this is just a bunch of edges being added. It's really simple. I tell this graph to find this vertex. This vertex returns a pointer to that vertex, to the vertex it finds, and this graph returns a pointer to the other vertex it finds. So unimaginatively, the data point I'm looking for is 1, and the data point here I'm looking for is 2. So all it really has to do is it goes looks up the object, the class instance in the graph that's node-based that has the data point 1 and returns a pointer to that class. This one does the same thing for the one that has the data point 2, returns a pointer to that class, and yeah, you're not going to be able to easily decipher it just by looking at those. So I made a PowerPoint. And here's the PowerPoint. As you can see, one connects to 3 different nodes. Those 3 different nodes connect to several different nodes themselves. 2 connects to 3 and 4 and 5. And then 5 and 3 and 4 connect to 7, on to 14, on to 15 and 16. Then from 15 to 20, or from 16 to 17 to 20 to 21. And it just goes in a nice cyclic path. None of these nodes actually dead end, and that's cool, but I just did it because even though there's 21 nodes here, there are significantly more edges. And to clarify, neither of my graphs are weighted, but they are directional. They're both directional. They're both actually identical to this design, implemented using a pretty similar method, but I don't alter the adjacency one like I did with the graph node based. I clearly know how to add the additional methods to the header class for the adjacency graph in order to give it the same functionality that the node-based graph has. But so it runs through that. It creates the first it creates the nodes, then it creates the edges for the nodes. Because of the way that the graphs are set up, you can't make an edge for a node until the node itself exists, because the graph is a dependent object of the node itself, or the vertex. So you can't have a edge without a node, because there's no place to contain it. I just reset begin, the graph size is, tells you what the graph size is, makes a clear indicator that the test is about to begin. I just declare these 2 in order to free up space to do proper line printouts. This one just goes ahead and finds out if such and such is null before it tries to use it, because we don't like trying to use null things. It's not good. And it just slips through there. When I was talking about how this is really nice, this is my solution for the graph dot, the wonderful graph node base. It does the exact same thing that this does, for the most part. All it does is it loops through the nodes and it prints out each and every one of the connections for it. And again, this is the same thing, except in between the 2, I remove the connector between 19 and 14. So to show you what that looks like, I don't want it to go from here to here, so I remove this line right here. That's pretty simple. Then I just run the test again, and then I decide to remove node 21 and connect 20 to 5 in its place. So what I do here is I delete 21, and then I make 20 point to 5 instead. So the way I actually do it process-wise in here is you can see I make 20 point of. I remove the edge for there. 20 stops pointing to 21. I remove the vertex for 21, so 20 doesn't end up pointing to null. And then I add an edge between 20 and 5. So first thing I do is I destroy this. I then remove this, which also removes the pointer or the edge going from 21 to 5 because I've destroyed 21. And then I make a new edge going from 20 to 5. And then I just run the same test again. Except I've decremented it by 1 because I've removed a node. And then here's the adjacency test. It is almost identical, except I don't have to push an instance of an already existing vertex into the adjacency in order to start it up, because if you look up here in the constructor, it is not overloaded. There's only one. I just declare the int get started. You just run it through the same kind of while loop. Then I create edges identical to this. And then I go down here and I print the adjacency list, which, like the other bit up here that I coded myself, just tells you what all the connecting edges are for a given node. And then I print the graph size. And that's pretty much it, because it's more or less identical, and with a couple added methods it would be completely identical to the node base. But for my project I used a unweighted directional graph, because you can only get from 1 to 3. There is no connection from 3 to 1 unless I make another edge. But yeah, it's very straightforward. And it's unweighted because even though you see them spaced out here, there is actually no weight individually for these lines. But hey, it works. And then we just go ahead and hit play. And we watch it zip through console. As you can see in here, graph size is 21, test begins. It runs through all of this. It ends. Okay, so it says here, the edge between 19 and 14 has been removed. So when we go up here, you can see 19 is connected to 11 and 19 is connected to 14. We'll go down here, and you only see 19 is connected to 11. And then we remove 21, so you see 21 up there, but you no longer see it down there. Constructing the adjacency list, made the graph vertices. Adjacency edges have been added, printing them out. Vertex 1 equals edges 2, 3, 4. Vertex 2 equals edges 3, 4. Vertex 3 equals edges 4, 7, 9. Etc., 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 and so on. Graph size is 21 because it didn't delete any, but there we go. And that concludes my presentation on making and using a graph. Even though the only thing I did with this one was create general functionality, I already know with absolute certainty that this kind of functionality can be used to do stuff like mapping roads, mapping connecting routes and travel routes through things like subways and the various connecting stations therein. You could use it for bus stops and everything else, and all you'd have to do to set it up would be to load up the various routes, and then you can interconnect like targets. You just have to be careful what kind of information methodology that you're using, because strings don't work the best for this. It's better if you enter in a string with an absolute UID, then you use the UID for the string rather than the string itself. I remember seeing this in object-oriented programming, analysis and design for Java, published by Headfirst. But yeah, and obviously you can use it for game AI. But if I was going to use it for game AI, all these would be weighted. All of these would have a more realistic spacing to them. They could be bidirectional, but each edge would be in its own unique instance. And if I was going to do that, it would probably be a more complex connector for it, because I would want the edges to be able to hold like a value, either a float, a single, or a double, in order to more accurately reflect it. And then I would use the really nasty equation of like these where, or the cube root, yeah, it's the cubed root of x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared. And this nasty thing gives you the absolute distance of something in three-dimensional space, which allows you to determine the value. And one of the things that you could do with that is that you could say when y2 is greater than y1, you can find the rise run of that. So if you find the multiple value of it, so if y is like 3 times, if the delta of y2 is such a value, you could say that it takes this much more effort, or, well, rise run itself is y2 minus y1 over x2 minus x1, and that determines your slope. So that would determine the steepness of your uphill gradient, theoretically. Though you'd have to kind of do a cross displacement by like z2 minus z1 as well, in order to get a proper displacement on that. But that would basically tell you your uphill slope, and then you could go ahead and turn around and use that as a multiple for determining the movement cost between two three-dimensional points, and thus the edge cost of it, so that your AI doesn't go steadily trickling up a hill just because it's quote-unquote shorter on one of the axes. And vice versa, if it ends up being a negative slope because the destination is downhill, you could also reduce the cost. So if you had, let's say 3 is uphill and 1 is downhill, but 4 is level. So even though 4 might be, say, further away, x-wise, x and z-wise, than 3 is, but 3 is up like a steep hill. Even if 4 is further away from 1 on an x and z axis, the cost of going to 3 would still be higher because 3 would be uphill. Now, conversely, even though, say, 3 and 7 are very close, but 7 is even further uphill than 3, well, the cost of moving downhill is much less because you're able to work with gravity. So it might well be cheaper to go down from 3 to 1 than it would be to go up from 3 to 7, even though their XY is closer. So that's kind of one of the considerations that you have to take into account. But yeah, that's neither here nor there. That's just real-world applications of what you would use the graph for. And I guess that just shows that I understand them, but I've been studying them for a couple of years, and they're really the bread and butter of AI. Because when you're starting to deal with like real-time strategies or any kind of complex movement game, you kind of have to have graphs as a part of your game engine's AI. Otherwise, your AI doesn't really go anywhere. And then you get into the fun part about where you have like it wants to get to 21, so it's like, okay, how do I get to 21? Alright, so one of the paths I could take is 1 to 3 to 7 to 14 to 15 to 20. However, I could also do 1 to 3 to 7 to 14 to 16 to 17 to 20 to 21. Or I can be really round about it and do 1 to 3 to 9 to 13 to 19 to 11 to 18 to 17 to 20 to 21. Right? But yeah. Or 1 to 2 to 3 to 7. Or 1 to 2 to 5 to 7 to etc. 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 So the pathfinding, what would make it easier and more consistent is with weighted edges. What makes it more sanity saving is the fact that I have monodirectional edges. So it can't go, oh, 2 to 1. Nope, because there's no edge going from 2 to 1. So I'm on 2. Okay, where do I go from 2? Oh, 3. Okay, or 5. And where after that? Well, pretty much only 7. Because 5 to 7 or 3 to 7. It saves gray hairs, but it doesn't really make sense in like an RTS setting that I couldn't go from 3 to 1. I just have to make sure that when the AI is trying to get from 1 to 21, that it can actually do so in an efficient manner. And if like 2 becomes blocked for whatever reason, it knows it can go to 4. So it can do 4 to 1, 1 to 4 to 7 in order to do the path as well, or 1 to 3 to 7. And this is helpful that it's able to find these paths, and when you start doing game AI, you'll see the path, the edges themselves actually, going onto a stack. So 1 to 3 will be an item on the stack, 3 to 7 will be an item on the stack, 7 to 14 will be an item on the stack, and then each of these is going to have an associated edge value. So the edge value of that is going to be put onto the stack, and then the total of the stack is going to be calculated in order to determine the cost of the path. It's kind of mind-numbing because the nodes themselves, when you're doing pathfinding, may or may not have a value. Because like if there's something particular on the node or contained in the node that merits taking the path, like if there's an apple or a treasure chest or something that would make a certain lure go to that specific node other than just its edge costs, that can be a factor. But when you're actually doing pathfinding itself, normally you're just looking at the edge costs. How much does it take me to get from 1 to 3? How much does it take me to get from 3 to 7, 3 to 9? Just those kinds of things. But yeah, this is just a very basic skeleton structure of what you have to have absolutely for a graph and for the vertex. And the only real addition that I could say that I do for this is that I would say I would put, like, say, if t now this is just really pseudocode. So this would just, you'd only be able to change the data on it if it was null or zero. Although with, templates you can't necessarily declare it being zero because strings don't typically end up being an integer. But hey. And that's just the main real problem that I have with it, is because this method exists right here, you could accidentally create nodes with the same ID. And that would be bad. Because if you deleted if you had two nodes that had the ID of 12, or the ID of A, the character, you could accidentally end up setting two nodes to have the same ID. And then if you go to remove one, you only get one, just because the way that the remove edges are. Because as soon as it finds the edge to remove, it leaves. That simple. So, yeah. You shouldn't be able to add an identical, but if you change an already existing one to be identical, then you're in trouble. But that does it for me. I'm now just rambling. Thank you for your time.